Our hope is that if the definition is correct,
at least good circuits, and actually only good circuits, when we execute them, we'll get the value we expect. They'll always finish executing, and we'll always get values that are defined at the end. Can we prove that? What strategy are we going to need to prove this? And it should have something to do with the two properties we said. It has to not have cycles. It has to be connected in the right way. That kind of means there has to be a path from the inputs to the outputs, and there can't be cycles. And if that's the case, well, this is the hint. So the book's definition has the same property that depends on there's some way of layering the circuit, that we can sort the gates in some order such that at each layer, the inputs are all in earlier layers, that you never depend on input in a later layer. If you had a cycle, you couldn't do that. But if you don't have cycles, you can sort the gates into layers in some way. So at each layer, every gate only depends on inputs from a previous layer. Right? And if you can define things in layers, well, then it seems like we're starting with an input layer defined. What are we going to need to do to prove that eventually we get the outputs defined? What kind of proof do you think might be useful here? Yeah. Yeah. So what are we doing induction on? It has to be a natural number. Remember, our induction principle only works for natural numbers. So what's the natural number that we're doing induction on? Yeah. Good. Yeah, the layers. We can number the layers. The book already did it for us. It said there's a function that maps each gate to a number, which is the layer of that gate. We're doing induction, where our induction predicate is that for all gates at layer n or earlier, the output is defined. You have a base case, which is the inputs, so it corresponds really nicely to our input, and our inductive case is always saying, if all the inputs of the previous layer are defined, we can define the outputs at the next layer.